Integration by parts is an integration technique which reverses the chain rule. I've written the product rule below so that you can see it. Now the first thing that we'll do is a bit of rearranging. We want to isolate the f of x g prime of x term as so. Next, we'll throw an integral sign in front of everything. We'll also use the fact that the integral of the derivative is just the original function. As said, the antiderivative of the derivative is just f of x g of x, and we don't need to include a plus c term yet since it's accounted for in the integral sign that remains. Now we're pretty much done here, but this is a bit cumbersome, so we'll introduce some notation to make this a little bit easier to swallow. Let u be f of x and v be g of x, so that du is f prime of x dx and dv is g prime of x dx. We'll plug all of that into our expression above, and it reduces to the integral of u dv is uv minus the integral of v du. This is called integration by parts. Now the entire goal of this is to take the integral on the left and to create a simpler integral on the right. If we write down what this transformation looks like, then we get the following. This looks as though we've taken the derivative off of the g and pushed it onto the f, and that's going to be a convenient thing to remember. Okay, to see this at work, let's integrate x e to the x. To apply our formula, the first thing we need to do is figure out which function should be u and which should be dv. There's often only one correct way to do this, but I'm going to do it both ways so that you can see what happens if you choose incorrectly. First up, let's take u equals x and dv to be e to the x dx. Since we'll also need to know du and v, we'll compute those now as well. Plugging everything into our formula, we get the following. Notice that the integral on the right side is just e to the x, which is pretty easy to solve. So doing that gives us our answer. Importantly, notice that once all the integral signs on the right-hand side have disappeared, then I include my plus c term because we're working with the indefinite integral. In the other case, we take u to be e to the x and dv to be x dx. Again, we have to compute du and v, so we'll do that. And substituting this into the integral gives us the following. Now this equation is still correct, but the integral on the right is way worse than what we started with. This suggests to us that this probably isn't the way to go, so we're going to stick with our first case as our only possible solution. But of course you're probably asking now, how do we determine which function should be u and which function should be dv? And if you look around, you'll find lots of little tricks which work most of the time but not all the time, or maybe mnemonics. But it turns out there's an easier way. And let me show you using our above example. Since we want the right integral to be easier to work with, let's see if we can just figure out what it looks like. The key is to realize that whichever function we set to be u will show up as du on the right-hand side, while dv will show up as v. This means that of the two functions that we start with, we must differentiate one and integrate the other. I'm going to set up a table where we can keep track of this, but if you practice it enough, you can eventually do it in your head. First, let's assume that we differentiate x and integrate e to the x. The derivative of x is 1. The integral of e to the x is e to the x. Doing this would give an integral of e to the x on the right-hand side. If we flip this and integrate the x while differentiating the e to the x, then our new integral is x squared e to the x. These are the two integrals that we found above. In fact, you can still see the x squared e to the x integral at the top of the screen. Now looking at these integrals, I definitely prefer to integrate the first one, so that tells me how I'm going to set my variables. The rule then is to let u be the function that you differentiated and dv to be the function that you integrated. We'll do an example very quickly here, but first I want to show you how to deal with definite integrals. The great thing about integration by parts is that the bounds of integration stay the same all throughout the application of the formula. So let's put this all together then. Let's integrate the following definite integral using parts. Now you might be tempted to set u equal x, since it's easy to differentiate, and you know that its derivative is simple. But let's see what the table tells us. The problem with differentiating x is that we would then have to integrate ln, and we have no idea how to possibly do that. So we're probably not going to go that route. Instead, integrating x and differentiating ln is not only doable, but gives us a surprisingly nice integral at the end of the day. So that tells us we're going to set u to be ln x, dv to be x dx, and then we're going to compute du and v as usual. And then integrating by parts gives us the following. I'm going to evaluate that first term and simplify the second like so. And doing the last integral and a bit of cleaning up is then going to give us the answer. Integration by parts is thus another very useful tool that comes from reversing one of our differentiation tools.